Hello everyone, welcome to Basic Chemistry Plus. And today, mainly we're going to talk about the standard electrode potential of the D and F block elements. In the last video, we have talked about the oxidation states. But let me tell you that today's video is one of the most important video because standard electrode potential is one of the hot topic of this chapter. So, first of all, we are going to talk about some of the important factors before we jump straight into the standard electrode potential topic. We'll be talking about the electrode potential, how is it coming, and what are the deciding parameters for which you see these type of absurd curve. First, you can see how much deviation is happening over there. The red line is something that should happen, and the black line is something that is happening. So, why these deviations are happening? This is what we are going to talk about in this topic, in this video. If you just look into this, the values over here, first it is decreasing, then it is again increasing from 1.18 again decreasing to 0.44, and now and it is completely a positive sign in copper. So it's a complete absurd phenomenon, which is absurd trend you can see over here, right? Now let's find out what is the reason behind it. First we have to understand what is an electrode potential. Here mainly we talk about the reduction potential because that is something taken as a standard for us, isn't it? So here we are going to talk about the reduction potential. So what do we understand by the word the reduction potential? Let's say there is manganese 2 plus ion and it is taking some 2 electrons to become Mn. Now this is a reduction process you can see over here because reduction is gain of electron, right? And oxidation is loss. So over here the E naught value of this particular reaction, let's say that's negative. Let's say. Then would the reaction happen? What do you think? The reaction won't occur because the value is negative. So what you have to do is you have to make it positive. Now you know that delta G equals to minus NF E shell from electrochemistry. And if the value of E shell is negative, then what would happen? Delta G, if this is negative, if this is positive, then the delta G would be negative. And you know for a reaction to be spontaneous, delta G have to be negative. So E shell have to be positive as well. Okay. Now see, in this process, all the E shell values are negative, isn't it? All of them. So what do they mean by this? It means if you want to convert titanium 2 plus, let's start with titanium. Titanium 2 plus plus 2 electron to titanium. If you want to do this, this reaction is not going to occur. What would happen then? The opposite reaction. Okay. So titanium to titanium 2 plus plus 2 electron. This is the reaction that would happen. And what will be the E shell for this? Positive 1.6. Okay. First we need to understand this. So all of them wants to go for a oxidation reaction. That's why their reduction potential is negative. Now, how the process of reduction happens? So first, M is converted into M gas, and that's for that I need sublimation. Delta H sub, solid to gas is called sublimation. Now, M gas is converted into M2 plus by giving IE1 and IE2 because I am considering 2 plus. If you have 3 plus or 4 plus, in that cases you have to just keep on adding the ionization energies over there, and from there you need delta H hydration to get M plus aqueous. Delta H sublimation is a positive value, like it's an endothermic process. IE1, IE2, they are also positive because they are also endothermic. You need to give energy, right, to take out the electron in periodic property. We have learned that. Whereas the delta H hydration, that is a negative value because you are going to get some energy from it. It's the exothermic process. We have learned all these things in thermodynamics. So now, if you don't remember what was delta H hydration, let's talk about that a bit. What is delta H hydration and how is it exothermic? Okay, this is a hydration energy. So when you hydrate something, that is when you hydrate something, that is the energy which that is coming out of it. Okay, that's called the hydration energy. That's a negative. That's an exothermic process. Okay, always hydration is always exothermic. Now the reduction potential that we are talking about, that is not only the only electron giving capacity, that is the addition of all of these energies, and you know that these are the sign of this particular energy. So if you just add them up, the total value E naught value would be coming from there only. So you have to add all of these factors up to get this. Now if you see, I have given the list where all the values are given to you. Now if you just check all the values for each and every metals, so let me just scroll left side a bit. Yeah, The ionization energies for titanium, it's ionization energy 1 plus 2 actually, but titanium is given as 13.09, right? Now you can see if you just move from left to right, the values are increasing. For copper, it is 1958, which is a pretty high value, isn't it? One of the highest value. And if you just go to the delta H sublimation and the delta H hydration for all of them, you do understand we need to add these three values up in all the time for chromium as well. We need to add these three values up, and let me tell you, if you add them, you'd get a negative value over here. If you add them, you'll get a negative value over here, a negative value over here. This is only the reduction potential. This is the value of reduction potential you're getting. If you just check, these are the values you are supposed to get in the list. Okay, the values that you can see, the first three guys have negative values, like we have found out over there. But see the copper. Copper has a positive E naught value, isn't it? So why is that happening? Now you just go to the copper section in the list over there. Let me just scroll down. Let me show you. Yeah. So if you can see, the copper's value is 1958. Now if you add that thing with 318, which is the delta H sublimation, 318, then you and if you subtract it with 2121, if you do this sum, this one, then what will you have is you have to have a positive value. Just do this and you find, you know. So that's why they are having a positive value. So this is not done by any one parameter. This is the outcome of three parameters. Now for Cu, ionization energy 2 plus delta H hydration is greater than delta H hydration. This should be ionization energy 2 plus delta H sublimation, not hydration. Okay. So copper is, that's why that's the one of the least negative. Zn has low delta H sublimation, but because of high IE1 plus I2, it has the negative 0.76 value over here. So for zinc, if you see the ionization energy, the delta H sublimation, this one is low. But because of the other factor, this is high. That's why we are getting a very low value. And after subtracting with hydration, we are getting a low value, which is just minus 0.7. So this is what we have. Now, the next topic would be the trend in the M3 plus to M2 plus. So far we are talking about M to M2 plus. Now we are going to talk about M3 plus to M2 plus. Now look into the list one more time. In that list, you can clearly see that titanium, for titanium the value is negative, for vanadium also negative, for chromium also negative, but the rest of three have positive value. Now first, let's understand what are they trying to tell you in this particular case. So let's say you have titanium 3 plus. You are reacting that thing with an electron. You'd get titanium, okay, just a second. Let me just rewrite it. It's not that visible. So if the reaction titanium to 3 plus taking 2 electrons, if they wants to become titanium plus, okay, 1 electron, titanium plus 2 plus, this reaction has a value of negative 0.37. So the value is negative. What does that mean? So we mean that means this reaction won't happen. Unlikely to happen because the delta G would be positive in here, isn't it? So all this reaction, all the first three reactions, they are not supposed to happen. So for them, what are we expecting? What are we expecting from them? We're expecting the opposite reaction to happen in this case. So just the opposite reaction. Titanium 3 plus plus electron. We expect that thing to happen now because that would have a positive sign now. Similarly for vanadium, similarly for chromium. Okay, for vanadium and chromium as well, that's the same thing. So opposite reaction would have the inert value. So this is having 22 atomic number. Let's find out why is it happening. 22 atomic number, so 3d2 4s2, right? So in titanium 2 plus it would be 3d2, 2 plus electrons would go on, and in titanium 3 plus this would be 3d1. So you know, because of the exchange energy interactions, because of the exchange energy interaction, this is right now 3d2. After, you know, in titanium 3 plus this would become 3d1, right? That is something you do understand now. Because of the exchange energy interaction, 3d2 is more stable than 3d1. Okay, so that's why 3d2 would be likely to be. So that's why titanium 2 plus is something. And for vanadium, we just think about it. For vanadium or for scandium, what is happening for scandium? Scandium, they're saying that the this wants to become Sc3 plus, and it has a very low value, means it wants to become Sc3 plus. And in Hc3 plus, it is getting the noble gas configuration. So let's find out what do they mean by that. So for scandium, what will be the electronic configuration if I write? Just a second. if we talk about scandium over here, in the figure you won't find scandium. There's a reason in the graph if you look, because scandium is 21, right? And scandium 3 plus means 3D. So we need to crisscross it. 3D1 4s2 is the scandium. Okay. Then if you talk about Sp3 plus, that means all the three electrons from here are gone, right? So it would become 3D0. So that's the noble gas configuration. That's why you cannot even see it in the graph, right? So that is the major reason behind this. Now, let's go for the Mn2 plus scenario. Okay, the manganese scenario. The Mn2 plus is a D5, so the value is so it is 25. 25 means it would be 3D5, 3D5 4s2. Okay, 3D5 4s2. So I'm just writing D5 in which ways. So 3D5 4s2 would be the uh, configuration. Now, once it's donating 2 electrons, it will be 3D5 in the end. Now, when you're talking about the D5, you know that this is very much stable, isn't it? So that's why Mn2 plus being stable, Mn2 plus won't go to Mn3 plus anymore. So that's why you can see that the value from Mn2 plus, Mn3 plus to Mn2 plus is positive. So they want to come back to Mn2 plus. So Mn2 plus, Fe2 plus, CO2 plus, they won't go to CO3 plus or Fe2 Fe3 plus because they are stable in this scenario, in this situation. Okay. So this is how you can just wrap it up. So whenever you see the positive values, remember that is always going to happen. And whenever you see the negative E naught value, that's not likely to happen in this way. Now, the third point is chromium. Now, if you just think about the chromium over here, chromium 3 plus, this is, we need to understand the chromium 3 plus in octahedral geometry. In octahedral geometry, you know that the d orbital, they just splits according to the crystal field theory. They would be splitting into T2g and the Eg. When we talk about chromium 3 plus, that is nothing but D3 electronic configuration, which means it would be T2g3 electronic configuration like this. So this is a very much stable configuration. You can see this and D5. D5 would be T2g3 Eg2. Both of them are very stable. So that's why manganese was also stable, Mn2 plus, and this is also stable. Now it's time we talk about the stability of the higher oxygen state. So you can see that with the metals, metals are very much stable with the halogens, and because of their high electronegativity. And that's the reactivity of our order of the halogens. It goes from fluorine to iodine. You can see that third transitional series and the second transitional series, they are getting stabilized. They are just being able to stabilize their higher oxidation states, not the first ones. Because in the first series, if you see chromium to zinc, they are forming stable difluorides. So that's CrF2, ZnF2. They are making difluoride, VF2, like this. They're not making higher oxidation state. But when you talk about fluorine, actually, fluorine has the ability to take it to the higher oxidation state, though. So they can form hexafluorides with fluorines. Okay, they can make it. But for other halogens, they would not stop in the difluoride. So for manganese, you can see it can goes to say to the 7. You can, I'm just calculating it real quick, and you can see x minus 6 minus 1 is equals to 0, so x equals to plus 7. Manganese oxidation state is plus 7. So that's also stable with fluorine and oxygen because they are very much electronegative. So, and the next point is after manganese, the tendency to oxidation state show higher oxidation state that decreases. Like for iron and cobalt, you can see they are making less, like trifluoride or trihalide, whereas for manganese it was hexahalide, right? So manganese can show higher oxidation state. Now, the tendency to show highest oxidation state is due to either high lattice energy of COF3 or higher bond enthalpy due to the higher covalent bonds, that is VF5 and CrF5. So actually what happens is, like in the higher oxidation state, their bond enthalpy as well as the lattice enthalpy, all these things are very high. Now, if you go to the fluorides, actually they are not that much stable when you put them under a low oxidation state metal. Like VF2 and CUF, when you talk about them, they are found, but otherwise, other than these two, you'd be able to see mostly they form the chlorides, bromides, and iodides generally. Okay, because fluorine is very electronegative, so it pushes the metals to the higher oxidation states anyway. Now, for copper 2 plus halides are known except iodide. So why we do not see the copper iodide? So actually what happens is copper oxidizes iodides to iodines. You can see over there in this reaction, Cu is plus 2 and over here it is turning into plus 1. So D9 and this is D10. So actually, when it's turning into D10, it is much more stable from D9. That's why it is undergoing that conversion. And in the meantime, iodine is helping copper to do that. So you know what? Copper is actually oxidizing iodine in order to make himself stabilized in this particular portion. Now, the formation of colored compound would be our topic in the next class. So the next class is going to be very, very important because we are going to talk about the LMCT, MLCT charge transfer, DD charge transfer, and all these things. So stay tuned, subscribe to my channel, and thanks for watching.